Hello, welcome to today's video where we are going to be looking at the process of diagonalization, which is a process that allows us to reduce a matrix to its diagonal form. This video will be split into three main parts. The first part will focus on how to do the process of diagonalization. In the second part, we'll show how we can use diagonalization to do other things. And then in the third part of the video, we'll actually look at why any of this stuff works, because I'm aware that's something that will interest some of you, and therefore those of you that applies to can stick around for that explanation. But what on earth are we even talking about here? Well, to explain what we mean by reducing a matrix to its diagonal form, we are talking about rewriting a matrix so that it is a diagonal matrix. And you might be wondering what that is as well, but the ironic thing is you've already been dealing with them, because the most simple example of a diagonal matrix is the identity matrix. Simply put, a diagonal matrix is any matrix where the only place that non-zero values are occurring is in what's called the main diagonal, which is the diagonal that goes from the top left to the bottom right hand corner of the matrix. All other numbers that aren't in the main diagonal have to be zeros in a diagonal matrix. On top of that, here's another example of a diagonal matrix, and also it's worth mentioning that all this stuff scales up for 3x3 matrices, 4x4 matrices, etc, etc. But why do we care about diagonal matrices? Well, the thing is, diagonal matrices are really easy to multiply together. For instance, if I'm multiplying this matrix by itself, you'll very quickly see that it's a quite simple task to do, because we're doing this row times by this column first of all, and that conveniently is arranged in a way so the 7s get multiplied by each other to get 49, and the zeros are conveniently lining up, so therefore it's just going to be that 7 times by 7 and no other contribution to it. And then we'd be doing that first row of 7 0 times by the second column, but this time the zeros are not matching up nicely, so it means all the things are being multiplied by 0, so we get 0. If we were then to do the bottom row then times by both those columns, again the bottom row times by the first column is just going to get a 0, but then conveniently that bottom row times by the second column means again the zeros do line up nicely, and then the non-zero numbers line up nicely, and so therefore we're just multiplying those together. Basically, the point is, if you are doing a diagonal matrix to a power, it's just the same as doing those diagonal elements to that power instead individually, rather than having to do all the faffing about with the rows and columns and all that sort of stuff. So it means 3001 to the power of 4 is just 81001. So very easy indeed to calculate stuff with. Now that's all well and good when you have a diagonal matrix, but what if you don't? Well, that's where the process of diagonalization comes from. It allows us to rewrite a matrix in terms of a diagonal matrix, thus making it easier to do certain calculations with. In order to diagonalize a matrix, let's call it A, then you need to do the following steps. You first need to find n linearly independent eigenvectors for A. And by n, I mean that the number of eigenvectors you find has got to be the same as the dimensions for your matrix. In other words, if you've got a 2x2 matrix, you need to find 2 eigenvectors. If you've got a 3x3 matrix, you need to find 3 eigenvectors, so on and so forth. You might note, though, I did say that these eigenvectors need to be linearly independent, which is absolutely fine most of the time, except for that annoying scenario where you've got repeated eigenvectors, and that repeated eigenvector only has one very specific eigenvector that goes with it. However, as that's not going to happen more of the time than it is going to happen, that's hopefully something you won't encounter too much. But it does mean, sadly, for those cases, you can't do diagonalization with those matrices. You are then going to take those eigenvectors and you're going to use them as columns to form a new matrix, which I'm going to call P. That's not the official name for it, but just for the sake of these notes, that's how I'm going to refer to it. Therefore, it means that this matrix P will always be a square matrix because, for instance, you're always going to have two 2D eigenvectors for a 2x2 matrix. So therefore, you'll get a 2x2 matrix for P. If you've got a 3x3 matrix, you'll have three 3D eigenvectors, so therefore that will lead to P being a 3 by 3 matrix, and so on. To then be able to reduce the original matrix A to its diagonal form, let's call that D, then you are going to then need to use the matrix P. Yes, I'm sorry, there's all these different matrices here. You are going to need to multiply the original matrix by the matrix P in the following way. You're going to need to do P inverse times by the original matrix times by P again. That will leave you with, guaranteed, a diagonal matrix. So, therefore, let's put that into practice, show a demonstration of it. So we need to reduce this matrix to its diagonal form. Step 1, we need to find eigenvalues, because that'll help us find the eigenvectors. So therefore, we are going to find the determinant of this matrix and set it equal to 0. So if we were to do that, we'll end up with the following pairs of brackets. And then we have to multiply all that stuff out. And if we were to do so, then we'll end up with this quadratic. That quadratic then factorizes very nicely, but you could solve it by any means that you see fit. We get the eigenvalues of 4 and 7. We can then use these eigenvalues to find eigenvectors by taking the original matrix, multiplying them by the unknown eigenvector xy, and setting that equal to an eigenvalue lot or multiple of that same eigenvector. So for instance, if we were to do that in this first case, we'd end up with 5x plus 2y is equal to 4x. And if you then rearrange that, you'll get x plus 2y equals 0. We've then just got to pick any values of x and y that satisfy that relationship. And so therefore I'm going to choose x equals 2, because then that means y just has to be minus 1 in order to make the relationship work. Of course, I have reminded you in previous videos, it's always a good idea to check with the other equation formed by multiplying that matrix equation out. So therefore, just to double check, we have the second row of that first matrix multiplied out to get x plus 6y, and therefore that must equal 4y, and that does also lead to x plus 2y equals 0, meaning the values we pick will also satisfy that. Then proceeding ahead to do the same with the other eigenvalue, we've got 5216 times by xy equals 7 lots of xy. That will get us 5x plus 2y equals 7x, which means we end up with minus 2x plus 2y equals 0. And therefore, in that particular scenario, that's quite nice because it means that 2x is equal to 2y. In other words, x equals y. So therefore, the other eigenvector in this scenario is 1, 1. Again, double checking with the other equation, we'd end up with x plus 6y equals 7y. And therefore, that would also lead to x equals y as well. Cool. So now we can form the matrix P by just using these two eigenvectors as the columns of it. So therefore, I'm going to rewrite this as 1, 1, 2, minus 1. It's worth mentioning there's no particular order you have to put your eigenvectors in. So I could have chosen to form P by putting my two eigenvectors the other way around, but still the columns have to stay as an entire eigenvector. So you can't mix and match, but the order of the eigenvectors as a whole can be swapped around. And therefore, now all I need to do in order to be able to reduce this original matrix to its diagonal form is to take that matrix, multiply it by this matrix P after it, and then also multiply the front of it by the inverse of P. That will get us the diagonal matrix D. So if we were to calculate that, that will get us 7, 0, 0, 4. Now, interestingly, you may notice that in our diagonal matrix, the elements that are non-zero happen to be the same as the values of the eigenvalues themselves. Is that a coincidence? No, actually, it's guaranteed to happen. Now, the reason for that is obviously something that has a proof, and I'm sure I'll make a video in my Prove It series at some point to show that, but for the moment, it's just something you can obviously use as a way of checking your answer. However, unfortunately, this is not a fact that you can use to skip the process of finding the eigenvectors and finding the matrix P, because the matrix P is really important for establishing the relationship between the diagonal matrix D and the original matrix, and then also what way around the two eigenvalues go in your diagonal matrix is decided by the order in which you place the eigenvectors to form your particular matrix P. And interestingly, that is all you need to know about how to do the process of diagonalization. If you wanted to do this process with 3x3s, it would be the exact same idea, but of course you're doing it with 3x3 matrices, so it's going to take longer to do, hence why I'm not going to do an example on that in this video. The only problem is that some of you might be looking at this stuff just thinking, well, okay, cool, but why are we allowed to do this? Because the matrix D that we found clearly isn't the same as the original matrix we had. So although the matrix D would be easier to do calculations with, it's not going to get the same result as if you did calculations with the original matrix. Well, that's the important thing to bear in mind. The matrix D by itself isn't representing the original matrix. We have to express the original matrix in terms of D and P. So how are we going to do that? Going back to that earlier fact that established what D was in relation to A, we could rearrange this fact to make A the subject of the formula. So we could first start off by multiplying the front of both sides by the matrix P. That'll leave us with PD on the left. On the right, the P and the P inverse will cancel out, meaning we're just left with AP. Then we could multiply the end of both sides by P inverse, which would lead to this fact here. So therefore, that is how we can express A in terms of the diagonal matrix D and these matrices P formed by the eigenvectors. And this is the really neat trick. If you're doing a matrix to a power, it's the same as just doing that matrix P times by D to that same power times by P inverse. It means that the P matrices don't get affected by the power, and therefore you're only having to apply that power to the diagonal matrix, which, as we already established, is really easy to do. Therefore meaning it's going to be much, much quicker than actually applying that power to the original matrix, particularly if you have a very awkward power or a very large power. So let's do an example of that to show that in action. Of course, if you've got a good enough calculator, this is something you could just type into the calculator in one big go, no problems. But if you're asked to do this by hand, that might potentially be a bit annoying to do, certainly if you're multiplying it by itself 6 times. So the first thing we need to do is to find the eigenvalues, so we can find the eigenvectors, which will help us find the matrix P. So determinant of this is equal to 0, therefore meaning 8 minus lambda, 3 minus lambda, minus 14 equals 0. Therefore, we have 24 minus 11 lambda plus lambda squared minus 14, leading to the quadratic as follows. Quite a nice one again, almost as if I purposely designed it that way. Therefore, meaning we get the two eigenvalues of 10 and 1. We can therefore use those to find the eigenvectors. So therefore, I'm going to do that now. Doing the eigenvalue of 1 first of all, let's do that. So therefore, we're going to end up with x times by 8 plus 7 times by y is equal to 1 lot of x. And also you would technically end up with 2x plus 3y equals y. However, both of these relationships are going to lead to y is equal to negative x, which is quite convenient, because it means the first eigenvector can be very simply found, and it's just going to be, for instance, 1 minus 1. Then proceeding to find the second eigenvector by doing this. Then again setting up the equations. And once again, conveniently, as often happens ultimately with the 2x2 matrices, you end up with both equations leading to the same relationship. In this particular case, we're going to end up with 7y is equal to 2x. What does that mean? It means that if, for instance, I pick y is equal to 2, then it means x has got to equal 7. And therefore, those are our two eigenvectors. Therefore, the matrix P could be found by combining these two eigenvectors together as columns. So therefore, we're going to end up with 1 minus 1, 7, 2. Cool, so therefore we can reduce our original matrix to diagonal form by doing the inverse of P times by that original matrix times by P again. If you were to work out what that will come to, it will come to 1, 0, 0, 10. But therefore we can now use that to work out what our matrix to this power of 6 is going to be by using the fact we quoted earlier, which is that a to the power of 6 would have to be the matrix P times by d to the power of 6 times by p to the power of minus 1, or in other words, p inverse more appropriately. So therefore we can go ahead and do that ourselves right now. So we know that 8, 7, 2, 3 to the power of 6 is going to be our matrix P times by the diagonal matrix to our power, which was 6, and then just multiplying by the inverse of our matrix P. And this is something you could then use a calculator to help you do, but the interesting thing about this process is it's meant to help you be able to do this with either only a numerical calculator at most, or maybe even no calculator at all if the numbers are small enough to allow you to do so. So therefore, in this case, applying the trick we mentioned earlier about taking diagonal matrices to powers, we just got to do 1 to the power of 6 and 10 to the power of 6, meaning we've got 1 and 1 million, because that's 10 to the power of 6. We could then also find the inverse of that matrix on the end, and therefore that would be having the determinant out the front, which would be 2 minus minus 7, and then swapping the 1 and the 2, and then multiplying the 7 and the 1, or the minus 1 I should say, by minus 1. So therefore get us a positive 1 there. And so therefore we can start multiplying this out. If we were to do that, we'd end up with 1, multiplying these first two matrices together, we'd end up with 1, we'd end up with 7 million, we'd end up with minus 1, and we'd end up with 2 million. Working that out, we're going to end up with a 1/9 out the front. We're going to have 1 times by 2, which is 2 plus 7 million, so that's 7 million and 2. We're going to have minus 7 plus 7 million, which is going to be the rather annoying number of 6,999,993. We're going to end up with minus 2 plus 2 million, which is also going to be rather annoying, 1,999,998. And then also 7 plus 2 million, which is 2,000,007. Now, conveniently, that looks like it's going to be really horrible, but it's not. We already should be expecting our answer to come to nice integers because the original matrix was only made with integers, so taking it to a positive integer power will lead to integers. and conveniently it does, leading to 777,778, 777,777, and 222,222, and 222,223. And there you go. We worked out what our matrix to the power of 6 was. Yes, it still ended up being a bit horrible to do, but what do we expect if we're taking numbers to larger powers? You're going to end up with large numbers in there. And as I said, this process starts scaling up and becoming more and more useful if you've got a very large power, or if you're just doing a particularly awkward power, things such as that. So as far as what we're covering today in this specific video, that's the full extent of what you need to know and how to carry it out. But you're probably wondering why the stuff we've been talking about today actually works. So I'm going to attempt to explain that stuff as well. First of all, starting off with the easier of those two things to explain, which is that most recent of the two results we mentioned, which is this idea that if you're taking a matrix to the power, then that's the same as just doing the matrix P times by just D, the diagonal matrix taken to that power, then times by P to the power minus 1 on the end. But why? Well, the easiest way to show what's going on there, to show why it's working, is to look at a specific example, let's say a to the power of 3. Because if you're doing a to the power of 3, and we've already shown that a is individually equal to P times by D times by P to the power minus 1, therefore we're taking all of that stuff to the power of 3 when we're doing a to the power of 3. Now, unfortunately, we can't just apply index laws here to apply that power of 3 to those three matrices individually, because the order of operations, or rather I should say the order of multiplication, matters with matrices. So therefore what we're actually doing when we're taking all of that stuff to the power of 3 is we're doing P times by D times by P to the power minus 1 times by P times by D times by P to the power minus 1 times by P times by D times by P to the power minus 1. And obviously if we're changing that power, you'd scale it up to whatever you want. But the crucial thing about this is you'll notice that as part of doing this, we've always ended up with a P to the power minus 1 immediately times by P, or to word it better, P inverse times by P. And then there we go in the middle again later on, P inverse times by P, which is really good. Because, of course, if you multiply an inverse by its original form, then you are, of course, going to get the identity matrix. And when we're talking about multiplying, the identity matrix effectively acts as if it was never there in the first place. So in reality, this stuff simplifies to P times by D. The P inverse P cancels out, leaving us with another D. And then another P inverse P cancels out effectively to give another D in the middle. And then we still have that P minus 1 on the end. P inverse, sorry, I don't know why I keep on calling it P minus 1. Anyway, the crucial part there is now we do have D times by D times by D, which, what do you know, would be allowed to be simplified to get D to the power 3. And so therefore, that is why the power ends up only affecting the diagonal matrix D rather than all of the stuff, just because of the way everything lines up quite nicely like so. And what about the other main talking point of this video, which was the fact that if you start with a matrix, multiply it by the matrix of its eigenvectors, then multiply the front of that by the inverse of P, you're guaranteed to end up with the diagonal matrix D, the original matrix in its reduced diagonal form. But why? Well, in order to understand that, you need to be aware of three main important facts. So just to remind you of those, they're all facts you should be aware of already anyway, but if you start off with a matrix and you multiply it by one of its eigenvectors, let's call that eigenvector V1, then you're guaranteed to end up with just the eigenvalue associated with that eigenvector, lots of that eigenvector. Basically, in other words, that's the whole idea of eigenvalues and eigenvectors. They are specific vectors that only get affected by a scalar multiple when applying the matrix to them. So that's an important fact to be aware of straight away. Another classic one is if you multiply a matrix by its inverse, you're guaranteed to end up with the identity matrix. And same goes for, of course, if you do it the other way around. They have to be right next to each other, though, admittedly. But if they are, then they do effectively cancel out. It's not the official terminology. Hopefully you know what I mean, though. And then the third factor I want you to be aware of is what happens if you start involving an extra scalar multiple. In other words, if you're multiplying by one number rather than the whole entire extra matrix as part of doing matrix multiplication. In other words, if you had two matrices, A and B, and that would come to a result of, let's say, C, doesn't matter what it is, but the point is, if you were then instead to do A times by 2B, the reality is that extra scale factor of 2, as it's only a scalar scale factor, it's something we can effectively take out the front. So this is the same as just doing two lots of AB, and therefore that just has the result of applying that scale factor to the answer that we had before as well. So these three facts together combine to explain this fact we're going to be looking at here. This is not going to be an actual full proof. I could do that in one of my prove it videos maybe at some point if people so wish. Let me know in the comments if you do wish me to prove it. But to give sort of an intuitive explanation of it, then the first thing to be aware of is when we're doing A times by P, that's effectively causing this situation here. I know P isn't actually the eigenvectors because it's now been turned into a matrix, but the crucial thing is the columns of P are the eigenvectors. And because P is the second thing written in that multiplication, that's important because when we're doing matrix multiplication, it's always rows in the first thing times by columns in the second thing. So when we're doing that matrix multiplication, it's almost just treating it as if there are only the eigenvectors there rather than a matrix anyway. We're just effectively multiplying the two eigenvectors separately and then pasting them together at the end. So therefore that is happening, but therefore the result you're getting from that is a matrix that ends up having basically two columns in it. That's not the proper notation for it, by the way, but I'm just trying to do something that sort of explains what's going on here. But you're going to end up with a eigenvalue, lots of the original eigenvector that was first written there, and then also another eigenvalue, lots of the second eigenvector. So it's basically just scalar multiples of the individual columns of what we had in that previous matrix P. Now we are then multiplying that result by the P inverse. And that means that the P inverse and P aren't right next to each other. So it's not as simple quite as doing this, but it is very similar because of the fact that in reality, I know we've got lambda 1 lots of V1, which was the first column of P, and now lambda 2 lots of the second column, which therefore wasn't just the original column we had for P. Because those are both just scalar multiples of the entire column, and because, again, still this result is still the second thing in this multiplication, we're still just going to be using the columns of this result when doing the matrix multiplication. So we're just going to be doing the rows of P inverse times by this first column, which is just lambda 1 lots of V1, which means, therefore, it's effectively the same as doing lambda 1 lots of P inverse times by that original column that was in P. Meaning, therefore, as we're doing the original rows in P inverse times by the original columns of, or the original columns of P, therefore that means you're just going to get the same columns you get when doing P inverse times by P normally, which is, of course, the identity matrix columns. But, yes, there's the scale factor, but we can multiply that afterwards. So therefore you're ending up with lambda 1 lots of 1, 0. If we're dealing with 2 by 2s, which is what I've sort of assumed in this explanation. And then you're going to end up with lambda 2 lots of 0, 1, because again, although that second column isn't the same column that you had in P, when we are looking at it, we realize it's just a scalar multiple of it, and therefore multiplying P inverse by that will mean that we are just taking that column back to that column that it would be for the identity matrix, but with that scalar multiple applied afterwards. Therefore, that means we just end up with effectively the diagonal matrix we wanted, but just these scalar multiples of the individual parts of it. Cool. As I said, that wasn't a full proof, but that is a sort of intuitive understanding of what's going on there. Also interesting, by the way, I use this sort of understanding of what's going on to help me remember all this stuff, because it's very easy to get confused, particularly with the other fact about which way around the P inverse and P go. When you're trying to find D, it's always the P on the end, because I'm aware and remembering that it's to do with this fact of the link between matrices and their eigenvectors. So you've got to create that property happening, which means you've got to have the A followed by the eigenvectors in order to make that happen. And then therefore for the other factors, remember, oh, okay, therefore if it's this way around for this fact, it's the other way around for the other one, due to all that rearrangement stuff. Okay, that is all I wanted to cover for today's video. I hope you found this video useful, and I'll see you in another one. Goodbye.